Welcome back. In the last lecture, we built the frame. Cryptography is a toolbox, and almost everything it does is mapped to 4 goals: confidentiality, integrity, authentication, and non-repudiation. If those 4 words don't feel solid yet, that's fine, because today we're going to be building upon them and we're going to make it real. We're going to take everyday systems that you already use, open them up, and watch those 4 goals and how they actually show up in real-life software. By the end, you'll do a short exercise where you name the goal behind the real features yourself. Let's start with the one you hit every single day: HTTPS. In lecture 1, I said TLS protects your connection. True, but let's go a layer deeper, because it protects a connection hides a lot of the actual reasoning. When your browser connects to the bank, 3 changes have to happen before any real data moves. First, the server proves who it is. By presenting a certificate your browser can verify. That's authentication. Second, the 2 sides agree on a secret key that only they know, even though they're talking over a network anyone can watch. And third, once the key exists, everything after it is encrypted. That's what confidentiality really is. So, the little padlock isn't one thing, it's authentication and confidentiality, set up in a specific order every single time. So I've used the word TLS a lot of times throughout this course so far, in the past lecture and this one, but I haven't really defined it. The TLS is a cryptographic protocol designed to provide secure communications over a secure computer network. This can be such as securing emails, or for example, WhatsApp has it as well. And here's the part that most people miss. TLS also gives you integrity. Every chunk of data sent over that connection carries a small tag that proves it wasn't changed in transit. If an attacker flips it even 1 bit, the receiver notices and throws it out. So a single HTTPS connection is quietly doing 3 of our 4 goals at once: authentication, confidentiality, and integrity. One feature does 3 goals, and that's the kind of mapping I want to get you guys to see automatically. Now let's talk about what happens after you log in, how your password is stored. This is where a lot of real breaches go wrong, so it's worth slowing down. You already know from the last lecture that passwords should never be stored in plain text. It should be hashed, meaning it should be turned into a fixed length fingerprint that can't be reversed. But hashing alone has a problem. If 2 users pick the same exact password, a plain hash turns them into the same fingerprint. An attacker who steals from the database can see those matches, and worse, they can pre-compute the hashes of common passwords and just look yours up. Plain hashing leaks a lot of patterns. The fix is something we call a salt. A salt is a random value added to each password before it's hashed. Same password, just different salt, completely changes the fingerprint. Let me show you why that one change matters so much to us. Because seeing it and visualizing it would help you guys a lot. Picture this: 2 users who both choose the same password hunter 2. With plain hashing, they produce the same identical hash. Let's say it starts with 45 and 87. An attacker can see the 2 matching fingerprints and instantly clock it that these 2 people share the same password, and they can crack both of it at once. Now we can see how this can be a problem. But now let's imagine we add a unique random salt to each one of the passwords before hashing. User 1's hash now starts with F2AC, while user 2's starts with 9B1E. Same password, but they have completely different outputs. The patterns are no longer recognizable, and the attacker cannot match the users. So the pre-computed lookup tables they may have had before are now rendered useless. One small random value completely breaks apart this entire attack. So when you're testing a system that stores passwords, this is a checklist forming already. Are the passwords hashed, not encrypted or stored in plain? Is one salted with unique value? Is a hashing function a slow one built for passwords like bcrypt or argon2 instead of a fast general purpose hash? You don't need to break the crypto to check these, you just need to know what it looked like. And now you do. Right. Now let's talk about messaging, because encrypted gets used very loosey-goosey here, and the details matter. When you send a message in most chat apps that are not end-to-end encrypted, it's encrypted in transit, so it means it's protected on the way to the server. But the company's servers can still read it. End-to-end encryption, like Signal and WhatsApp use, is different, because the message is encrypted on your device and can only be decrypted on the other person's device. This means that your message stays completely private. The server in the middle just passes along scrambled data that cannot be read. So when someone says it's encrypted, the real question is, encrypted from who? In transit protects you from outsiders on the network, while end-to-end protects you from even the people running the service. Now let's move on to software updates, which is some of the goals that people forget. Non-repudiation plus integrity. When a vendor ships an update, they sign it with their own private key. Your device checks that with a signature against their public key before installing anything. This falls into integrity because if a single byte of that file is changed, this signature fails. And it falls into non-repudiation because only the real vendor holds the private key, so they later can't deny that they shipped it, and no one else can forge it. This is why tampered updates get rejected automatically. The signature is a proof and your machine makes sure to check it every single time. Now let me show you what proof actually looks like, because you'll run into it. A JWT, a JSON web token, is everywhere in modern web apps. It's a great example of a signed object you can actually inspect. It has 3 parts separated by dots: a header, a payload with claims like who you are and when the token expires, and a signature. The first 2 parts are just encoded. They're not encrypted. Anyone can read them. The signature is what matters. The server signs its token, and on every request, it checks that signature. If someone edits a payload to make themselves an admin, the signature no longer matches, and the token is rejected. Integrity and authentication in a string you can paste into a debugger and read. Okay, here's where you start doing the work. I'm going to give you guys real features, and your job is to name the security goal or goals behind each one. Pause the video, say your answer out loud or write it down, then play to check it. The whole point of this course is to make sure that you can actually do it yourself. So, if you're ready, this is how it works. I'll name this feature, you pause, you answer it, and then I reveal it. Now let's begin. First one. A website loads over HTTPS. It's confidentiality and authentication. It's confidentiality, so no one on the network can read your data, and authentication, so you know you're talking to the real server. Second, a downloaded file comes with SHA-256 checksum you can compare. SHA-256, for some context, is a cryptographic digital fingerprint. Integrity. You're confirming that the file wasn't changed. Third, you log in and the App Store checks your password as a salted hash. Confidentiality of the stored password, even if the database leaks. Fourth, a signed software update. Integrity and non-repudiation. We talked about this one before. I'm not going to touch on it a bit too much, but yeah. Okay, so let's do 4 more. Fifth, a JWT in your session, signed by the server. Integrity and authentication. 6, an end-to-end encrypted chat. Confidentiality, even if it's from the server itself. 7th, an SSH key you use to log into a server. And just to remind you guys, SSH key is secure encrypted access credential used to authenticate your identity. Authentication, proving who you are even without a password. And 8th, a digitally signed contract or document. non-repudiation, and integrity. How did you do it? If you got the most of them, then you already have a lot of it down. Give yourself a pat on the back if you did. And that's the real takeaway from the first two lectures. The 4 goals aren't, tricky. They're really simple. Once you learn that you can look at them, look at any feature and ask, what is it protecting and how would I check it? You started thinking like someone who tests and builds secure systems, not just someone who heard his word. From here, we're going to go under the hood, and the next section covers just enough math to understand how these tools actually work. And I promise it's not going to be that much math. I made sure that it wouldn't. I'll see you guys there. Bye.